I've drawn here a macroscopic object. This is at initial time and then some other time later. You can see it's isolated, not touching anything else. And inside it, it has one-dimensional elements, these little pink squares called oscillators. And inside, and I have 6 of them. Here's initial state, and another time later is still the exact same system, still the same number of oscillators in it. That doesn't change. But what I've shown in here is I have what's called quantum, like energy. So each one of these little square oscillators can have some quanta energy levels. It can't be a fraction, it has to be a full amount. And so inside this isolated system here, I've shown I have 7 quanta energy levels at this time, and each one of these oscillators is going to get some number of those quanta levels. So here this one got 3 and 0, etc. At some other later time here, the same system, here's how the quanta levels distributed among those oscillators. So we'll talk about this now. The thermal energy in a macroscopic object, for example that, can be randomly distributed among its particles. So I can put the quanta anywhere inside an isolator. We can model an isolated system, so that's this, as a collection of one-dimensional oscillators. And Einstein showed us that there's 3 one-dimensional oscillators in one atom. And each of these oscillators, each one of these little squares, can have a discrete number of quanta energy. Can't have a fraction, a discrete number. And the higher the total, both of them times I showed 7, but if I had more at one time, I would have 8 versus 7, so something would have changed in the system. But the more number of those that there are, the higher the total energy of the system. Because each one of these has a discrete same number of energy unit quanta. And we can arrange the quanta among the isolators in something called microstates. And so this is a microstate. So one period of time, one moment of time, this is what it looked like. This is another microstate. And each one of these microstates is as likely to occur as any other microstate in an isolated system at a given macrostate. So given this, this is just as likely to happen as that. Now from statistics, we know the number of ways to arrange these quanta energy levels among n one-dimensional isolators is given by this formula. And for a previous video, remember that energy versus this quantum state of an atom, that we have these discrete energy levels, and the difference between energy levels here in this one-dimensional oscillator system, that difference in energy, that there's a quantum difference. It's this exact same difference in these energy levels between this state and this state, and this state and this neighbor, etc. And that energy level, so is that one quantum is the h bar times the angular frequency of this atom, where the angular frequency is the square root of the stiffness of the atom divided by the mass of the atom. So that's one quantum. And so having low energy levels associated with cold, and so if I put heat transfer into the system, then I can go from more cold to more hot. Now more microstates give you more entropy, and the definition of entropy is S is defined as this Boltzmann constant, which is units of energy per temperature, joules per kilogram, times the natural log of this number. And we know the entropy of a closed system never decreases. That doesn't mean if I have 2 parts and they're together that one part's entropy can't go up and down. The other one, one can go up or down, but the two combined, or the whole system combined, the entropy never decreases. And so their entropy final is always greater than entropy initial of the system. And the best we can do is reversible, where the entropy stays constant for the system. Now we'll talk about the relationship between entropy and temperature. So if 2 objects, for example, I have 2 different macroscopic objects that are in contact, and they each have their own personal number of oscillators. So they're a certain size. They're not sharing oscillators, but they're in thermal contact, but they share quanta. Then they're statistically most likely to range, so the total quanta in the matter, this range of total quanta in matter such that the associated largest number of microstates exists between the two of them. And the most probable distribution of quanta is the one that maximizes total entropy. And this graph kind of shows that I have a picture here. I have block 1 touching block 2 initially. Block 1 has more oscillators, it's bigger. So let's say it's 60%. It has 60% of the oscillators of the total system. So block 2 smaller. And now this oscillator number doesn't change. That's how big it is. What can change is the quanta level, which is how many bits of energy are in each one of these. So let's assume at time, initial time, that 90% of the quanta are in B1 and 10% are in B2. And so if I do this arrangement here, just thinking about B1, if B1 can have anyway from 0 of the quanta all the way to 100% of the quanta, and the more quanta it has, the bigger this number is going to be for gamma 1. And I showed this in the pink line. So the more quanta are in B1, the more there is. And then for B2, kind of drawn the opposite direction. If the B1 has the quanta, then B2 can't have them. So they have to add up to be 100%. So here this way, if B2 only has 0 of them, then it has this number 0. And then as B2 gets more and more quanta, its entropy goes up. And at the initial time, there's a lot more entropy in B1 than there is B2, but the slope here, so B1 has lots of quanta. It's hot. B2 has very few quanta. It's relative to what it can ultimately have, so it's cold. So the quanta relative to the oscillators, and kind of the slope here, the slope of this entropy is shallow for the hot one, so it can give up some and still not have much change in entropy. The slope on the cold one is steep. If it gains a couple, it's going to go a lot up in entropy. So the system is going to want to try to have B1 give some of the quanta to B2, because what that's going to do is it's going to make, that's a more likely distribution. So as it starts giving it away, there's more and more likelihood that that's the probability of what's going to happen. So it's going to shift to this point where the slopes are equal and the total entropy of the system is constant. And so this kind of understanding of this hot and cold and how two different macro objects having in thermal contact work together help us with this different temperature, which 1/T is the change in entropy over the change in energy, which is kind of related to this slope. And then for near constant temperatures and a small heat flow, the change in entropy is Q/T. So if I'm near a constant temperature, I put heat into the system, then the entropy goes up. And also we kind of know that for the heat transfer equals this specific heat times mass times delta T, kind of a general macroscopic thing. The specific heat capacity for an atom is the change in the energy of the atom divided by the change in the temperature. And so if I have a collection of atoms, the change in energy of the system is the number of atoms times this change in energy per atom. And at high temperatures for a solid, the specific heat capacity for an atom is approximately 3 times the Boltzmann constant as the temperature increases. The Boltzmann constant is also very helpful in looking for, if I have like a small system, an atom, or some small system that's connected to a very, very large system, I can find the probability of finding that has achieved an energy level in this small system. What's the probability of finding that? And the probability of finding that energy level in the small system when attached to this big system is given by the product of two things. The first one is this term, which is the number of microstates that this energy level exists at. And the second one is multiplied by e to the minus whatever energy I'm looking for divided by Boltzmann's constant and the temperature. And you can think about here, I plotted this term right here. So this probability, so let's say this was the number of microstates is 1. I plotted this as a function of this coefficient here. And what it shows us is if I'm looking for a very low energy level and E is close to 0, my probability of finding is very high. But if I'm looking for higher energy levels, my probability becomes worse and worse. And if as far as temperature, if I'm looking as I raise and raise the temperature, then this term right here, the probability becomes closer and closer to 1. So it's more likely to find that energy level at high temperature than it is at low temperature in this small system when attached to a large system reservoir.